So we are going to wrap up the exponent rules today. First one is the zero exponent rule, and the second one is the negative exponent rule. So these have their own definitions. So the zero exponent rule says that if you have any base with the power of 0, it's always going to equal to 1. So what this means is no matter what the power is, no matter what the base that the 0 power is on, it's always going to be equal to 1. So you may be asking, why is it always equal to 1? So I'm just going to do a quick example down here. We have to go by the definition of a number divided by itself is always equal to 1. It doesn't matter if it's a letter divided by itself, it's always going to equal to 1. So it doesn't matter if it's a decimal, something divided by itself is always equal to 1. So based off of that fact, we're going to be seeing why does the power of 0 give us 1. So let's say I have x to the power of 7 over x to the power of 7. This is equal to 1 because they're the same thing on the top and bottom. Now if I were to use the quotient rule with this, the rule is we subtract the exponent, 7 minus 7, and that gives me x to the power of 0. Therefore, this problem and this problem are both the same. They have different answers, which means that this answer here has to be equal to that one in order for these two problems that are the same to give us the same answer. So this is where the definition comes. Something divided by itself is always 1. If we use the exponent quotient rule, that gives us the base to the power of 0, which is also equal to 1. So that's just a quick little recap as to why this rule is true. Second rule, the negative exponent rule, we actually went over it last semester. So remember, if anything has a negative power, we can move it from the numerator to denominator or vice versa. So it says if a factor in the numerator or denominator is moved across the fraction bar, the sign of the exponent is changed from positive to negative and negative to positive. So you can make exponents negative if you want, but we prefer to have them always in positive form. So let's go ahead and see these two rules in action in A through H examples. So let's go ahead and start with A. So we have negative 3x all raised to the power of 0. Using our definition, anything to the power of 0 is always going to equal to 1. So this is just quick answer, 1. Next problem looks very similar to A, but it's slightly different. It does not have parentheses, whereas this one, the negative 3 and the x are raised to the power of 0. In this second example, the power of 0 only belongs to the x because technically the 3 has an invisible power of 1. Therefore, the power of 0 does not belong to the number negative 3 because it has its own power, an invisible 1. So in this case, only the x to the 0 is 1. So this really becomes negative 3, and the x 0 is actually 1 because this part right here, x to the 0, has the power of 0, and that equals 1. So this stays negative 3 as the final answer. So parentheses are very important. Next one, we have a 6 to the power of 0. That's also equal to 1. So everything inside the parentheses becomes a 1. Next one, we have a negative exponent. We always want to make negative exponents positive. So this is technically in the numerator if you write it in a fraction. So you move anything across the fraction bar to make it a positive power. So if I want to make that 8 to the first power a positive, negative first power, we move it to the bottom of the fraction. So in this case, it's going to be 8 to the 1 on the bottom. You can ignore that 1, but we have to put a space holder on the top, and it's always a 1. So this just simplifies to 1/8. Next one, same idea. We're going to move the 3 to the negative 2 to the bottom of the fraction bar, which makes the exponent its opposite into a positive. We fill in the top with a 1. Same thing here, negative 5th power. Everything inside those parentheses is going to move down, so 3x. We have to keep the parentheses to the 5th power. It becomes positive. We've space filled it with a 1 at the top. Next one, we're going to move the x negative 3 to the bottom. The 7 does not go down with it because it's not within parentheses, and it has its own exponent, remembering that there's always an invisible 1 for something that does not have a power. So only the x cubed goes down, becomes a positive. And instead of putting a 1 at the top, we put the 7 because it's actually already there. So we just keep the 7 at the top. Next one, we're going to go ahead and do the same. So the 3 to the negative 1 goes to the bottom. The 7 stays there. It doesn't have a negative power. It has a positive power of 1. So the 7 stays at the bottom, but the 3 comes down, and it has the first power on it. It goes from negative to positive. We space fill the top with a 1. But 3 to the first is just 3, so we can actually simplify this one. So we're going to put 1 over 7 times 3. The 1 can be ignored at this point, and we can simplify that to 1 over 21. All right, so this is just a basic idea of how to use the exponent rules for 0 powers and negative powers. So now we're going to do a mix of all the rules. So we're going to be simplifying all these expressions from I through the end, because we want to see how do we apply all the rules at once in different random problems. Remember, we always want to make sure our final answers can only have positive exponents. So as we're working, we want to make sure final answers have positive exponents. So let's go ahead and get started. Let's go and look at letter I. So we have 10 divided by 5. So regular numbers, you apply the regular operation. That's going to give us 2. And we have 2 options for the A12. We can either subtract them and get 0, and that becomes a 1, or if something is the same on top or bottom, it can cancel. So let's go with the canceling. It's a lot faster. We can cancel the A12s, and we're just left with the answer 2. So that's probably the fastest way of doing it, or you can subtract the exponents, and then a to the 0 goes away because it comes a 1. Next one, we're going to go ahead and take our 4 and 10. We're going to reduce the 4 and the 10. So I can divide these by 2, so it's going to be 2 over 5 when we divide by 2. Now for the b's, we're going to subtract the powers. 2 minus 4 is negative 2. The c's, I'm going to subtract the power using the quotient rule again. 5 minus 3 is 2. And for d, we're going to subtract the powers, remembering that it has an invisible 1 on it. So we're going to have 1 minus 2 is negative 1. Now we're going to go ahead and rewrite this with all positive exponents. So I'm going to put my big fraction bar. 2 stays on top, 5 goes to the bottom. Since b has a negative power, it's going to move from the top of the bar to the bottom. So it's going to become b squared at the bottom. C squared stays at the top. And d to the negative first, if I want to make it a positive power, it has to move across the fraction bar to the bottom. I'm not going to put the 1 because it's not needed. So this is my final answer right here. All right, let's move on to k. So before I start using the quotient rule, I need to use the power to a power rule. So this 2 on the outside gets distributed to both the 6 and the g. So it's going to be 6 squared. G to the 4 times 2 is 8. That's power to a power rule. The bottom stays exactly the same for now. Now I'm going to start reducing this. So I know that 6 squared is 36. I'm going to keep G8 for G10. Now I'm going to divide 36 divided by 4. That divides nicely, so that's going to give me a 9. And I'm going to go ahead and subtract 8 minus 10 is going to be negative 2. Therefore, the g to the negative 2 needs to move to the bottom of the fraction bar. So it's going to become a positive g squared. And the 9 stays at the top. All right, next one we have 15x9 over 5x6. Again, I can reduce 15 and 5 with a 3 and subtract the 9 and the 6, but I should realize this has a 0 power on it, so there's no point in doing all that work. I know that this whole thing, no matter what this simplifies to in the inside, is all going to become a 1 at the end. So that one's pretty straightforward. Let's go into the last 3. So we have to first simplify the numerator before we start doing quotient rule and dividing things out. So 3 times 8 is 24. And we have k and k3, so we're going to use the product rule. So we're going to add the exponents, invisible 1 here, so that's going to be k4. And denominator stays the same. We're going to go ahead and divide 24 divided by 2 is 2. And the k4 cancels with the k4, so they're gone. Or you can use the quotient rule, comes up with the same answer. And let's go ahead and work on that one. So here we can just start reducing. We can divide these by 5. So we're going to divide by 5, we get a negative 1. So I'm just going to put negative 1. Again, you don't actually need the 1. Denominator, we have 20 divided by 5 is 4. Let's start using the quotient rule. But actually first we can actually eliminate the A3s because they both have the same power. So let's use quotient rule of C. So C, 3 minus 4, we get C to the negative 1. And D squared stays at the bottom. There's nothing that's going to happen to that one. Let's go ahead and further simplify this. We have a negative power, so the C to the negative 1 moves from the top of the fraction bar to the bottom. So we have negative 1 over 4. I'm going to put C first just to put them in alphabetical order. And then D squared, although order doesn't matter. Last one, we're going to multiply the numerator and then use the quotient rule. 9 times 2 equals 18 at the top. A and A4, so we use the product rule, so 1 plus 4 because we have that invisible 1, A5. B5 and B7 we add, product rule again, that's 12. Denominator is 18, A5 and B12. Realize that the B12s cancel, so do the A5s, and 18 divided by 18 gives me 1. So that one's one that everything cancels out. All right, this is pretty much a general idea of applying the rules for zero exponent, negative exponent, and going back to the rules from before. So go ahead and start your practice, and good luck.